So we have looked at how we solve systems of linear homogeneous differential equations with constant coefficients with two variables, a two-equation system. Well, what about a three-equation system? Well, it's the same way. So consider this one here. We've got three equations. We've got an x, the y, and the z. We set it up just like usual. You know, we've got our a here. We've got our a minus lambda I. And what we want to do is we want to get the determinant of the a minus lambda I so that we can find those eigenvalues. And we do that. We go about to find the determinant, by getting our pivot, this one first, and then we get the determinant of this, okay? So I've got this right here. And we go through the whole process until we get down to this. Okay? So when we get down to this point, we start doing a bunch of algebra. First thing I did was factor out this -1 minus lambda. Okay? Got down to this point. Now notice right here, I've got just a 1 there. I multiply out this business, combine everything inside here, and I get this. And now I've got, and notice I factored a 1 out of this. So there's the 1. So now I've got this, which I can factor this as lambda minus 3, lambda plus 2. Okay? So this gives me 3 lambdas. Lambda 1 is -1. Lambda 2 is 3. And lambda 3 is -2. Now, what I do with those is I go back and, like before, I find my eigenvectors. First of all, for lambda equals -1, I put that back into the A matrix and set up this thing where I have my eigenvector here, and I get this system. Now remember, we can't just solve this system for K1, K2, and K3 because it's dependent. So what you proceed this way. Like I have, first of all, I notice K2 equals 0. Okay, so notice that's a given. And then I go down here and I find out that K1 plus 3K2 plus K3 equals 0. Well, that means that K1 equals -K3. Well, if I let K3 be 1, then K1 is -1. And I get my first eigenvector. By the way, I'm making this video outside, so you might hear birds singing, and I just heard a car honking. So there you go. Now, let's look at when lambda equals 2. Same situation. But now we get this system, and I proceed, I notice that from this equation, I notice that K2 equals 4K1. I just let K1 be 1, see? And then I get K2 is 4. Then I go to the next step and I say, well, -4K3 equals -3K2. K2 is 4. I got that from up here. Therefore, K3 is equal to 3. So I get my second eigenvector. Then I go to -2. Same business, same process, and I get an eigenvector to be 1, -1, 3. So at this point, I'm ready to set up my general solution. I got K1, K1, and lambda 1 was -1. Lambda 2 was 3. And here's K2, and so forth. So I've got my eigenvectors and eigenvalues, put them together to make this little solution right here. This is the general solution. So you can see that using this method for a 3-variable system is a little more challenging than the 2-variable. But that's the process.